This is the June 2009 Regents Chemistry Solutions. We'll start with the multiple choice and we'll end with a link to the part 2 free response. So let's get started with number 1. Let's be crazy and go in order. All right, so number 1. Let's make it nice and big. Which subatomic particle is negatively charged? Okay, well, you're dealing with 4 basic subatomic particles that we deal with in this course: electrons, neutrons, and protons. Positron is a piece of antimatter, which is the opposite of an electron. Now, if you don't know your particles, table O is your friend here. So if you got this wrong, okay, let's gander on to table O. And here is table O, and some of your chemistry teachers might have used this only in nuclear chemistry, but I find it very useful, okay, when we deal with particles, whether we're in nuclear chemistry or not. So if you notice, you got alpha particle, which you've already probably learned is a helium nucleus. It's got a mass of 4. Top number is the mass, and then the bottom number is the charge, or the protons, okay? So in any case, 2 protons and 2 neutrons, right? Protons and neutrons have the same mass. And how do I know that? Look at this. A neutron has a mass of 1, and a proton a mass of 1. Now, a beta particle is essentially a high-speed electron that's sent out of the nucleus. So this is an electron. And as you can see, it's given a mass of 0 and a charge of -1. Now, in truth, its mass is about 2,000 times lighter of a proton neutron. So we give it a 0 because its mass is insignificant. So if you can see, is the only particle listed here that has a -1 charge is a beta particle, which you should know is essentially an electron. So an electron is negatively charged, if you did not know that, and it's essentially the same thing as a beta particle. So number 1 is an electron. Number 2, which element has the greatest density at STP? All right, well, looking strictly at density, I'm looking at these atoms: barium, beryllium, magnesium, and radium. Something looks very common to me, and these are all alkaline earth metals. If you look in the reference table, you'd see beryllium, you'd see magnesium, okay? We'd skip some metals, and we would have barium and radium. And calcium and strontium certainly is in the same column. But my guess is as we go down the reference table, we're adding more layers of electrons, but more importantly, adding a lot more protons. So the elements get heavier as you go down. A lot more neutrons and protons as you go down. So just by looking at the group, if I had nothing else to look at, radium would be my choice. The molecular masses increase steadily throughout the reference table, so the ones with the higher atomic number. Now, if we look at the reference table, let's do that. And here we go. And there are our 4 elements. Okay, alkaline earth metals, group 2. So radium has an atomic mass to the radioactive elements. Go there. Beryllium is 9, magnesium is 24, barium is 137.3, and radium is 226. So you can see that the atomic masses steadily increase because of the greater number of protons and neutrons. So my guess would be radium, but you don't have to guess because there's another place you can derive an answer from, and that's table S. Let's go there. So table S lists a bunch of different things. First, ionization energy, the energy to pull electron away, electronegativity, the attraction, the melting and boiling point, these physical phase change temperatures, and density, atomic radius, and of course atomic number and symbol. So if we look down and find our elements that we're dealing, beryllium, okay, the one with the least number of protons and neutrons, has a density of 1.85. Okay, then we're going to have magnesium right here with 1.74. It's got a little more. So we can clearly see our differences here. So beryllium is 1.85, magnesium, okay, is 1.74. And let's go back down. We're skipping calcium and strontium. So we're going to find now our other elements here in this group. We got barium, 3.62. Okay, it's steadily increasing. And then we have radium. Okay, and our radium, if I can find it, is atomic number 88 is has a 5. So as we suspected, the element with the greatest density is the one with the greatest number of protons. Now that's not always going to work out, but certainly in a column of metals, that is a trend that we do see. Okay, so just to be sure, look it up at table S, you have that. So radium is the most dense. So choice 4 is the answer. Number 3, what is the mass number of a carbon atom that contains 6 protons, 8 neutrons, and 6 electrons? Now, the key word here for me is atom. Atom's always neutral. So they gave me 6 electrons, 6 protons. That makes sense to me. And I'm dealing with carbon. And if it's got 6 protons, we should know that it's going to have a 6 here. And we're looking for its mass number, right? This is the atomic number, right? That's the number of protons and electrons if they're neutral, and atoms are always neutral. So the positives equal the negatives, the positive being protons. And of course, the electrons are the negative particles, equal in magnitude but opposite in charge. And then carbon, its mass number is going to be all the particles that make up mass. Now, those particles include protons and neutrons, right? These are the two, okay, that have the mass in the atom. And if you forget about that, we can go to table O. Let's do that. So table O gives us the mass numbers of an atom. Look at the neutron has a mass of 1 and a proton has a mass of 1. So they have the same mass. So when we have neutrons and protons, they collectively give us the entire mass of the atom. Notice beta particles, which are electrons, do not. So taking what we know from table O, we can see that in the periodic table they give you some hints. The atomic mass number is a top number. Now from table O we know the neutrons have a 1 up top and the protons have a 1 up top. So collectively these are the protons and the neutrons. Let's go back to the question. Okay, so we've got 6 protons, 6 neutrons. They want the mass number. I was playing around with this notation they use, but clearly all we need is 8 plus 6 is 14, okay? And that will give us the answer. Number 3 is 3, the mass number, and we're dealing with this carbon-14. And sometimes they'll write that out as C-14, where this number, the proton number, is implied because the carbon is there. Only the carbon symbol has 6, so the mass number is 14, so choice 3. Number 4. Number 4 states which element is a metalloid. All right, metalloids are these chemicals, or these elements, I should say, that have properties of both metals and nonmetals. So they kind of separate the periodic table between metals and nonmetals. Okay, so let's go to the periodic table to show you where the hints are for this question. So this is the periodic table given to you in your reference table, and you can see that there is a black staircase here that separates these chemicals here, which we should already know are nonmetals. They're the smaller atoms that attract their electrons. They tend to become negatively charged by looking at their oxidation states because they attract electrons so well because of their high electronegativity. And then we have the metals, which are the compounds that are to the left and down of the separator here. And these guys, of course, tend to be positively charged, tend to lose electrons, tend to oxidize. Nonmetals tend to reduce as they gain electrons. But these atoms here that separate the nonmetals from the metals are your metalloids. And these elements here, okay, are your metalloids, sometimes called semimetals. They have properties of both. They're the kind of go-between, in-between, or the separator between the metals and nonmetals. So which of the 4 choices represents this compound? Let's go back to the question. Well, which represent these elements on the staircase, including Ge and Sb, germanium and antimony. So we've got aluminum, we've got argon, we've got gold, and we've got arsenic. Which one of these are on that staircase, or that's separated between the metals and nonmetals? Let's go see. So aluminum, although close to the staircase, is not a metalloid, okay? So that is not going to be the answer. Gold, hey you, is also to the left of that staircase, not going to be a metalloid. And of course, the answer, of course, argon, I'm sorry, is also that noble gas, not going to be considered a metalloid. And of course, arsenic, As, that's the choice you want to pick. So arsenic, choice 3, that's your metalloid. Number 5. Which substance can be decomposed by chemical means? If you're decomposing by chemical means, that means you're breaking bonds. You're breaking bonds and forming new ones. So you have to be bonded. You have to be something where there's a bond between elements. You look carefully, number 1 is aluminum. That's an element. Xenon is an element, and silicon. All of these are elements, and you should know that elements are the group of the same type of atoms. Okay, same type of atoms. And we know they all are distinguishable, okay, or they all differentiate themselves by the proton number. The proton number is the social security number of each of these. But octane is not an element. Okay, you should know from your organic course, oct means 8 carbons, and if you draw 8 carbons in a row, okay, 1, 2, 3, 4, 5, 6, 7, 8, ane means they're single bonded, and then you have to fill in the rest with the H's, as this is a hydrocarbon, a saturated hydrocarbon. This is a compound, and compounds are 2 or more different atoms chemically bonded. So you can break octane. Octane would be C8, and if you know your, by having an ane, the general formula is CnH2n plus 2. So I would double 8 to 16, this would be 18. Now you don't have to know this for this problem, but that is the chemical formula of octane. And carbon and hydrogen are 2 different elements bonded, unlike choice 1, 3, and 4, which are the same elements hanging out. All right, this can be broken down into 2 different elements, where these are already elements. Okay, so choice 2 is the answer. Number 6. Okay, an element that is malleable. Now, malleable is a property, a physical property of elements that can be heated and shaped into any shape without breaking. Okay, malleable. The word mallet is in there. It's that you can hammer it into thin sheets. Okay, and that's a property of metals. Metals can be heated and shaped very well because of their metallic bonding, their sea of mobile electrons. And a good conductor of heat and electricity, if you're a good conductor of heat and electricity, what you have is mobile electrons, which means you have electrons that are not held very tightly. If you're conducting electricity, you have to have electrons that are able, have an ability to be repelled or moved back and forth. So if I put a negative charge here, and you've got a bunch of electrons in your compound, these electrons have to be able to move to repel other electrons. And these would move, and therefore charge would be conducted across the object. So you have to have free moving electrons, and free moving electrons are from elements that hold on to them loosely. And metals, by all of these hints, are what you're looking for. They hold on to electrons loosely, which means their electrons are able to move throughout the atom very well, which means they're good conductors of motion since their electrons can move. And of course, they have charge, so they're good conductors of electricity. And the malleability, okay, is the reason why they can be shaped into anything, because they hold on to electrons loosely, but they have this sea of moving electrons in all directions that each nucleus of a metal can attract. And that's why they're malleable. So they're screaming to you, you've got a metal. Okay? Now, if you didn't quite get all that, nonmetals do not conduct heat and electricity very well. They're good insulators because they hold on to electrons tightly. Therefore, the electrons are not free to move as much, so they can't conduct motion or charge. All right? As I'm whistling through this, okay? It's like I have a big hole in my tooth here. Okay, any case, so I'm looking for metals. Now, atomic numbers, 16, 18, 29, and 35. Which one of these is a metal? Let's go see the reference table. Okay, so we have copper, atomic number 29, only copper has 29 protons. We've got sulfur, atomic number 16, argon, atomic number 18, and bromine, atomic number 35. Now, of course, the answer is going to be copper because it seems to be different from the rest. But remember, if you looked at previous questions, this is the divider between the metals and the nonmetals. The nonmetal area, of course, is above the staircase, and the metal area is to the left. So what's the divider is these what? Semi-metals or metalloids. Okay? So clearly, above and to the left of the staircase where atoms get smaller and hold on electrons tightly, these are the nonmetals. And of course, here's your copper, who is clearly a metal if you did not know that, okay, from experience. Okay, so atomic number 29. So number 6 is choice 3. Of course, that is copper, the only metal there. 6 is 3. Number 7. A 1.0 mole of sample of krypton gas has a mass of what? So looking for the mass of krypton that equals 1 mole. Okay? And that represents its atomic mass. You may say, well, why? Well, that's a mole concept kind of a lesson here. And I have plenty of those, okay, in my crash course series. Okay, but very quickly, krypton, if we go to the periodic table, let's go there. So krypton has an atomic mass of 83.79, and if you didn't know that, nice little reminder here is the atomic mass on your periodic table is given to you. They show you that's the mass number, and the atomic number, the proton number. Okay, so the hint here is that krypton has a mass of 83.79.3. And the reason this works is because when they were dealing with equal quantities of matter, trying to figure out a universal container that would have the same number of particles, they picked 22.4 liters because that gave us the actual mass, okay, the relative atomic mass in nice whole numbers. Let me explain. For instance, if I had 22.4 liters of oxygen, it'd be approximately 32 grams. Now the reason why it's 32 is because oxygen is diatomic, it bonds with itself. So if you have O2 molecules, if I have a box of oxygen, we know oxygen exists as this diatomic element, it exists as 32 grams that would fit in that container. So they made that container that it fits into called a mole. And that represented some number of particles because they wanted to be able to match particles. And using Avogadro's hypothesis, equal volumes, equal number of particles at the same temperature and pressure, they were able to take gases and compare the masses. When they put a box of hydrogen, okay, H2 at 22.4 liters at standard temperature and pressure, and it really doesn't matter, but they kept it at STP, standard temperature and pressure, as long as both gases are under the same conditions of temperature and pressure. They figured out that this box was 2 grams. This box weighed 32, and the ratio is a 1 to 16. Notice this is a 16 approximately, and of course the reason for the decimal place is because we're using, or the average, the other isotopes, and that's the most abundant. If you look at hydrogen, it has a mass of approximately 1. So they used that relative difference between the gases, okay, to come up with the actual mass per 1 mole. So they saw that there was 16 grams in this container and 1 for each hydrogen atom. Again, I'm dividing by 2 because these elements bond with themselves. So they actually got the relative scale based on each other of how much more massive oxygen is to hydrogen. Oxygen is approximately 16 times more massive than hydrogen. That's why the hydrogen has a 1. And they said, why don't we just use 22.4 liters because a box of it equals 16. So they chose 1 mole to equal this. Okay, so that when you wanted a certain amount of oxygen, okay, what you did was you just used the relative atomic mass. And that's a nice system. We made it that way. So obviously 1 mole of krypton, if I had a box of krypton, 22.4 liters of it, would be 83.8 or 83.798. Let's go back to the problem. So 1 mole of krypton is 83.8 3.7 grams per mole. Okay, and of course, it rounds off to 84, choice 4. Number 8. An atom in the ground state has a stable valence electron configuration. This atom could be an atom of what? Now, stable valence electron configuration means that we are dealing with a noble gas. Noble gases, the exception of helium, which holds 2 electrons in its energy level, is filled. Other noble gases will follow the octet rule. And the octet rule, very simply, is having 8 electrons. Okay, feeling that S and P orbital makes makes elements, which wind up being gases, I guess, makes elements very, very stable. Okay, so let's look at their atoms here: aluminum, chlorine, sodium, neon. So what we're really saying is which one is a noble gas. Now, noble gases are in group 18. Okay, so let's go to the periodic table and let's see who's got that stable octet. Here are my noble gases. Here's helium. It has a stable 2, okay, because it holds 2 electrons. And then everybody else wants to have that 8. Look at neon, 2-8, argon, 2-88, krypton, 2-188. They all have that 8. There's something special by having 8 electrons on the outermost shell. Sometimes those 8 fill the energy levels, okay, but otherwise, okay, so helium and neon have completed first energy levels, okay. Well, helium has the first energy level filled, and neon has the second one filled, okay. Argon and the rest don't have filled energy levels, but they have that special 8 where they fill this block up to the 8th, and that makes them very stable, low energy. The reasons why atoms become ions are to achieve that stability, okay? For instance, oxygen wants to gain 2 to become like neon. Fluorine wants to gain 1 to become neon. So oxygen makes 2 bonds because it needs 2 more electrons. It's 2-6. Nitrogen's 2-5 needs 3 more. That's why it triple bonds with itself. It needs 3 more electrons. Or it's the reason why it becomes -3. Carbon in organic chemistry makes 4 bonds. Why? It needs 1, 2, 3, 4 more electrons in order to achieve stabilities. And again, it's not part of the question, but they're all attached here. Sodium becomes +1 by losing 1. And why does it do that? 2-81 becomes 2-8. So sodium, when it loses an electron, the driving force why these guys become ions are to lose enough electrons to become as stable as a noble gas. Sodium loses 1, 2-81 loses 1, and has the same configuration as neon. So the only one here that is a noble gas that has a stable electron configuration or a stable valence electron configuration is our only noble gas, neon, choice 4. Number 9. Number 9, an atom of an element, now already an element, has a total of 12 electrons. So I'm picking from something from the periodic table. And an ion of the same element has a total of 10 electrons. Now, by saying the word atom of an element, that was key to me, because that let me know that I was dealing with a neutral substance. So if I'm an atom and I've got 12 electrons, that means I'm -12, okay, in my outermost energy levels outside the nucleus. If I'm an atom, all atoms are neutral, so collectively they have a charge of 0. So they would have to have in the nucleus +12 to do that, which means the only thing in the nucleus that's positive is protons. So there are 12 protons. That was key. Okay, now if an ion, now the word ion means charge, means now the atom is either negative or positive, depending if it lost electrons to become positive or gained electrons to become negative. Now, the same atom element has a total of 10 electrons. So it started with 12, and now it's got a charge, or at least the charge outside the nucleus is now -10. So how did it go from a -12, -10? Well, it must have lost 2 electrons. So you have 2 electrons less. Now the nucleus is still +12. You're not going to lose or gain protons. That'd be nuclear chemistry, not where this part of the course or these questions are. Number 30 and 28 is the nuclear questions. Any case, so we lost 2 electrons. The proton number outnumbers the electrons. So what's going to happen is this lower number of electrons can't fight off the +12, so it pulls it back in. So this ion is going to be smaller than its atom. Okay? So if I draw it down here to make more sense, here is the atom that was neutral. Protons equal electrons. And then when it became an ion, having lost 2 electrons, the ion is now smaller and +2. It gets smaller. And if you don't like the reasoning that I gave you in terms of, hey, now the protons, because they both still have 12 protons. They're both still +12 in their nucleus. But by having less electrons, this +12 can now overcome those electrons and pull them in tighter. Now, if you don't like that, anytime you lose weight, you get smaller. So if you lose electrons, you get smaller. If you gain electrons, now electrons would outnumber the protons and pull away. These are what nonmetals do. You get bigger. So gaining electrons, you get bigger. Losing electrons, since we're clearly losing electrons, okay, like losing weight, you get smaller. Nice, easy way to remember that. So let's look at our choices here. The ion is positively charged. Absolutely. You lost negatives. It's oxidation, right? Oxidation is losing electrons. So it became positive. If you remember from your redox unit, your charge number is going up because you're losing negatives. So the ion is positively charged. Absolutely correct. And its radius is smaller than the radius of the atom. That's the winner for me. Okay? So if you said number 2, you got it half right. The radius is larger. No, it's going to get smaller. You lose something, you're going to get smaller. So number 9 is choice 1. Number 10, which formula represents a nonpolar molecule? Now, a nonpolar molecule is not the same thing as a nonpolar bond. I have so many students over the years, they hear the word polar and nonpolar, they don't understand bond versus molecule. We're talking about the entire molecule. Now, if a molecule is polar, what that means is, if I draw like a shape here, if this is a molecule, it's linear, that means the negative side has more electrons than the positive side. Positive side is positive because of a lower number of electrons. There's more electron density on this side, so this side is more negative. This side kind of has a lower number of electrons, so it's less negative or positive. And these are poles, okay? And to create this unequal distribution of electrons, we come up with the first requirement for polar molecules. That's very important. You must have a polar bond. Now, a polar bond is an unequal sharing of electrons. For instance, I believe hydrogen has electronegativity of 2.2, chlorine 3.0. So because 2 different elements have 2 different levels of how well they attract electrons, if you look at the Lewis dot diagram of hydrochloric acid, you will see that chlorine has 1, 2, 3, 4, 5, 6, 7 valence electrons, and hydrogen has 1. By sharing, hydrogen feels like it has 2, which fills its energy level. By sharing, chlorine feels like it has 8. However, look how I drew this. I drew it so this pair actually is closer to the chlorine side because chlorine is more electronegative. So even though I may not have drawn as well as I wanted to, but these pair are definitely closer to the chlorine side. So this side of the bond, okay, this side of the bond is definitely more negative than this side. And we've created polar bond. All right, 2 different unequal sharing. 2 different sides of the bond are different. One side feels like it kind of lost electrons, Okay, one side feels like it gained electrons, and you created a negative and positive side of the bond. Now, why do we need that again? We need to have this unequal distribution to create a positive and negative side throughout the entire molecule. Now, the second requirement that we need is you have to have, must have, this is must be polar, must polar bond, okay. You must have, let's put must, why not? Must have, implied, asymmetry. Now, if you're asymmetrical, that means your polar bonds do not cancel. Case in point, okay, CH4. CH4, all right, very symmetrical molecule. It has 4 polar bonds, like carbon and hydrogen, 2 different nonmetals. The one with the great electronegativity, which would be carbon, pulls that pair closer. Remember, a dash represents a pair. This side of the bond is negative, this side is positive. So this has 4 polar bonds. So it fills the first requirement, but because of its symmetry, which I like to explain the same all the way around. I mean, I know it's not perfect, but it does work for this type of course. Okay, the same all the way around. These 4 polar bonds, or 4 vectors, however you want to explain it, cancel themselves out. A tetrahedral shape, okay, will provide a very symmetrical. So all you have to think is same all over. So these 4 polar bonds cancel themselves out. You can also say that, hey, because they're unequal in all directions in their sharing, in every direction, then they're equal in their unequalness. So their unsharedness, or their density of electrons, which is uneven in these positions, becomes even in all positions. Now, number 1 is the answer. It has polar bonds, and because of its symmetry, they cancel themselves out. So if you look at the postulates here, you must be a polar bond. Okay, good. This one has it. It's to be a nonpolar, to be a polar molecule. Okay, so these are the postulates to be a polar molecule. Must be asymmetrical. Well, this is symmetrical. So this does not fit the bill to be a polar molecule. Okay, number 2, hydrochloric acid, as we have drawn here, is a polar molecule because it has a polar bond and is asymmetrical, not the same on both sides. Look at water. Now you may think water is linear, but because of this lone pair, water is bent. So therefore, water is not the same all the way around. If you were to have H's here and here, or even just one H here, it would work, but my friends in chemistry, this bent shape is not symmetrical, okay? So this is an asymmetrical shape, definitely polar bonds, 2 different H's, so it's also a polar molecule. And ammonia, okay, if you do a Lewis dot diagram, looks a lot like this. So it has polar bonds, and it is also asymmetrical. So these 3 here are all polar molecules because they follow these 2 rules to be polar molecules. Okay, so methane is your answer, choice 1. It's a nonpolar molecule with polar bonds because of its symmetry. Okay, it's the only one there symmetrical. Now, to be a nonpolar bond, as we didn't talk about here, just as a review, that's like chlorine bonded to chlorine. This would be a nonpolar bond sharing electrons equally, and if you have a nonpolar bond, you can never be a polar molecule. So something to go over there. So number 10 is 1. Number 11, a compound XCl is classified as ionic if X represents the element. Okay, so ionic, this is something you desperately need to know, is made of ions. It's the bonding between ions. So it's a positive ion attracted to a negative ion. The question is, how did that occur? How do we make a positive ion? Well, we should know from redox that a positive ion is made from elements losing electrons. Okay, now something that's negative gain them. So an ionic compound is made between 2 elements where one is good at losing electrons and one is good at gaining. And there's something called a transfer, something you desperately need to know. So it's a transfer of electrons, and this occurs because there's a huge difference in the ability to hold on to electrons. You should know metals. They basically are large atoms where electrons are farther away, very far away from the nucleus. Okay, nonmetals. Nonmetals, okay, electrons are held much more tightly to the vest, so to speak. They attract electrons more. So nonmetals have a high attraction, or we would say a high electronegativity. And metals have a low electronegativity. They don't have much attraction because they're bigger in terms of their electrons being farther away. If the electrons are farther away from this positive nucleus, that means they don't have much of attraction. So metals tend to lose electrons because these electrons don't feel the nucleus as well as nonmetals do, because these electrons are so far away, so much more farther away from the nucleus than the nonmetals here. So we say the metals lose electrons and nonmetals gain. Or back in redox, we would say metals tend to oxidize and nonmetals tend to gain. Metals lose electrons, and they lose electrons, become negative, and become positive. Nonmetals gain. So when you put these two together, okay, metals and nonmetals, somebody who's weakly attracted to electrons and someone who's very strongly attracted to electrons, there's going to be a transfer. So if you've got sodium with 1 valence electron and you've got chlorine, who's got already 7 but is highly electronegative, it's not only going to take this electron, it's going to rip it away from the sodium. Sodium's going to lose it gladly. And when that happens, okay, sodium, okay, this is a Lewis dot diagram. So sodium's going to lose its valence electron, become Na with no valence electrons, and become +1. And chlorine started out with 7, and now is going to have the 8 by gaining, because it was a great difference in electronegativity, and it's negative. So it's a transfer because of a huge difference in electronegativity. Now if you look up electronegativity, sodium's about 0.9, and I believe chlorine is 3.0. Huge difference. So it's going to be a transfer. The analogy I give in class all the time is if you have my son, my 3-year-old, and you have me, and we have a tug of war every morning before I leave. Okay, and this tug of war is, this could represent the valence electron. Well, I'm going to pull that rope away from my son every time because I'm such a strong man. Well, I'm just an adult and he's a child. So of course I'm going to pull the rope away and say, who's your daddy? But the most important thing here is that I can pull this rope away from my son because I'm so much stronger for that rope than my 3-year-old. Of course he wears gloves. Okay, any case, that transfer of the rope is due to the huge difference in electronegativity. Now, covalent bonding, even though this question wasn't on it, but hey, I'm talking about everything today, okay, is sharing electrons. And why do you share between nonmetals? Well, nonmetals are both what? Strong. So if we're doing covalent bonds, we're forced to share because everybody's strong. No one's so much stronger to pull the rope away. So they're forced to share. So in any case, I'm looking for a metal here. A metal who would have a low electronegativity. So of my 4 elements, one's a metal. Now rubidium is the metal, but if you did not know, we have hydrogen, iodine, and bromine. Let's go to the reference table. Okay, here we are with the periodic table of elements in your reference table, and we had hydrogen, iodide, bromine, and rubidium. Now the staircase here that separates the nonmetals, the smaller atoms that attract the electrons, from the metals, which, okay, hold on to electrons loosely, and we know that they do that because if you look very closely at all your metals, they all become positively charged. They all tend to lose electrons. Now, the only misnomer or disclaimer I should say here is that hydrogen seems to be to the left of the staircase. This dividing line of metals and nonmetals are the semimetals or the metalloids. And you may think, well, because hydrogen's way over here, it's a metal, but no, it really belongs with the nonmetals. And what gives it away is the fact that it can become -1 charged. It can lose electrons. I'm sorry, it can gain electrons, okay, that -1 charge. If you look carefully, all these nonmetals above the staircase have at least one oxidation state that show negative, which means they tend to gain. Whereas no metal, okay, becomes negative. All right, and if you look up the electronegativity of hydrogen, being around 2.2, it's so much greater than the rest of these. So hydrogen is a nonmetal. So the only metal we have to the left of the staircase is rubidium. Back to the answer. Questions? So rubidium is our only metal, choice 3. Number 12. The chemical bonding in a sodium phosphate is classified as, all right, well, the first thing to realize is that this is a salt. This is an ionic compound, and you should recognize this because you see a metal in front and you see a polyatomic ion at the end. Now, a polyatomic ion is a cluster of nonmetals, okay, that have a charge. And if they have a charge, they're going to attract this positive metal that loves to lose electrons. So this essentially is sodium, which is a positive ion, attracting a phosphate ion, which is -3. Now, if you don't recognize this as a cluster of nonmetals, you need to go to table what the heck is that, which I call table E. Why is that what the heck is that? Because you may say, what the heck is that group of nonmetals? So we're going to go to table E. And I just want you to be able to recognize where to go when you see something you don't recognize or it's a cluster. So if you see basically if you see 3 or more elements, go to table E to see what that cluster is if you're not recognizing it. So let's go to table E. So here's what I call the what the heck is that table, and here's your cluster of mostly nonmetals that have a charge, okay, when they are grouped together. Now, of course, I said mostly. There are some exceptions to that, but I just want to show you where to look, okay? So phosphate, PO4, is -3. So this group of nonmetals somehow bonds and has a -3 charge. Sodium being a metal, and we know that it's a group 1 ion, and here it is from your periodic table in your reference table. It's a group 1 ion. Look here's a staircase separated between the nonmetals and the metals, and here's sodium, an alkali metal, and what charge does it like to become? Clearly, it likes to become +1. It likes to lose 1 electron and become stable as a noble gas. So this thing, you see a metal and a cluster, clearly it's a salt or an ionic compound. Now there's one little catch here. We know that the sodium and the phosphate ion, okay, are going to attract each other ionically, okay, because these are ions. This positive one, and look at there's 3 of them. It makes a lot of sense now that we would need 3 of these to attract 1 of these, because this would make a +3 altogether, and this would be 1 -3, and the whole thing is a neutral compound, as compounds are written. And you've done some of this in chemical naming. Now, interesting enough, so let's write the Na as a +1 ion, and this whole bracket. Now we use brackets in our electron Lewis-dot diagrams for ionic compounds to show that there's no sharing, that this is +1 exclusively, and this whole thing is -3. However, so we know the ionic bond is between the ions, but in this special case of polyatomic ions, you've got nonmetals bonded to nonmetals. So inside the cluster, we have covalent. Now, this is an advanced structure, one which you would not be able to do based on the curriculum, or not be asked to do. But phosphate, okay, I'm just count these, has 1, 2, 3, 4, 5 valence electrons. Each oxygen has 6. Now, again, this is called an expanded octet, not part of the curriculum, but phosphate, okay, is going to need 1, 2, 3 electrons to make this stable for the oxygens and for the phosphorus itself. Again, this structure, not part of the Regents curriculum, but I'm trying to show you that between the nonmetals, there is sharing of electrons. These are covalent bonds. Nonmetals are covalent, metal and nonmetals. So here's the ionic bond, but here's the covalent. So anytime you've got a polyatomic ion in an ionic compound, inside the polyatomic ion you've got covalent. So these structures are unique in our course because they both have covalent within the polyatomic ion between nonmetals. They're forced to share because their electronegativity differences are similar, okay, and ionic because between the ions they attract each other. So both covalent and ionic. Number 3 is 12. So which element is composed of molecules that contain a multiple covalent bond? Well, let's start with chlorine. Chlorine bonds with chlorine, it's diatomic. All right, this is which element is composed of molecules? Well, these are all what I say Hofbrinkels. These are part of those diatomic elements that love to bond with themselves. Hofbrinkels, and they love to bond to their H2, O2, F2, Br2, I2, N2, Cl2. These are your diatomic elements. So they bond with themselves. This chlorine has 7. Okay, and the other chlorine has 7. So borrowing one from each of them make each of them very stable. These are 2-8-7s. Okay. And by sharing one electron, they both achieve a noble gas configuration. So they satisfy the octet rule, so therefore only one bond was necessary. We look at fluorine, same idea. Each fluorine is 2-7. So this fluorine has 7 valence electrons, and all the halogens, when they bond to themselves, you can clearly figure out, are going to make one bond. Each one has 7. By sharing one, they're forced to share because they both have high electronegativity. They're nonmetals. Okay, they only have one pair of electrons between them, which is one bond. Okay, and we have hydrogen. Now hydrogen is a little bit different because it's in this first energy level, so it only needs 2 electrons to feel stable. So each hydrogen has 1, and by putting them together, it's a nice pairing because one each for each of them feels like they have 2 electrons by sharing. So you can see that, so fluorine, chlorine, and hydrogen won't work, and nitrogen has 5 valence electrons. So it needs to share 3 more, so you can figure out that this nitrogen is going to make a triple bond. And again, the reason why this works nicely is by sharing 3 more electrons from another end, this nitrogen feels like it has 1, 2, 3, 4, 5, 6, 7, 8, and this nitrogen feels like it has 8. So they satisfy the octet rule by gaining, or at least feeling like they gained 3 electrons by sharing. So the N2, okay? And there are some others that are Hofbrinkels that have multiple, and you should recognize them. Oxygen, okay? Oxygen has 6 valence electrons, so I draw 2 O's here, change up my colors. No, 1, 2, 3, 4, 5, and 6. And then this oxygen, 1, 2, 3, 4, 5, 6. And I did a multiple bond here, a double bond, because by sharing, this oxygen feels like it has 8, and this one feels like it has 8. So these are both 2-6, so they need 2 more electrons to be like 2-8 and fill the octet rule. These guys over here were 2-5. They needed 3 more. And you can see this from the periodic table. See, fluorine and chlorine are 1 away to become stable. So when they share 1 more electron with themselves, they both feel like they're 2-8. So they're 1 away, so 1 bond away. Oxygen, 2-6, needs 2 electrons to feel like it's a noble gas configuration by sharing 2 more. So with itself, it needs a double bond. Nitrogen, notice this is 1, 2, 3 electrons away to be shared. That's why it makes a triple bond. So interesting enough, the periodic table gives you some more hints. So number 4 is the answer. Which equation, number 14, which equation represents an exothermic reaction? Now exothermic means that heat is exiting. So that would mean that the heat would be on the product side if in fact this was exothermic. But we don't know that. We also know that exothermic curves start out with the reactants, this potential energy curve, and start lower, or end up lower, I should say, with the products. Now, why did that occur? Well, because energy was given off, the products have less energy. And the difference of where you start and where you finish, we call that change of heat or enthalpy. So we need some delta H values. If they put the heat in their reactions, we'd be good. But we don't have that, so we're going to have to look up delta H. Now, if it's exothermic, we're starting with something with high energy and going to low, and that makes sense because I'm giving off energy, so my products have to be lower in energy, more stable. So I'm looking at a value, a change in energy going down, which means this delta H is going to be negative. So the only place where we list delta H's is table I. So we're going to have to look for these reactions in table I. So here's table I, list of 3 different types of reactions. The first ones are combustions, which are all very exothermic. The delta H is negative, which means energy is being released. Okay, and then the second ones are, okay, the reactions formation or synthesis reactions. Okay, and then the last ones are, the last third here, are ionization reactions, where we have a solid dissolving with water into its ions. Now, we're looking for the reaction, and I've checked off the reactions that were in the problem there. We're looking for reactions exothermic, and you should know it's negative because energy is being released in our potential energy curve. But if you forget, they tell you in the bottom of this table, okay, that a minus sign indicates an exothermic reaction. So let's go look at the checks that I made. Ammonia chloride is one of your choices, breaking apart into ions. It's positive. That means that the products have more energy than the reactants because energy was absorbed. Okay, KNO3, breaking apart into ions, is also positive. And by the way, if these guys dropped into water, the temperature of the water, okay, would drop because both of these reactions absorb energy from their environment, especially the water, to make products that have more energy. So all endothermic reactions, positive delta H is because the energy is going up, the change, okay, make the temperature colder. A little aside there. And of course, this guy is also endothermic, and here's our winner, the exothermic reaction, okay, which would make the environment temperature go up because it's releasing energy into the environment. Okay, so there's our winner. So the only one with a negative delta H from table I is number 2. 14 is 2. 15. Standard pressure is equal to, well, we have an atmosphere, a kilopascal, 273 atmospheres, 273 kilopascals. Why don't we go to table A that lists standard pressure? And here we are, standard pressure 101.3 kilopascals or 1 atmosphere. Let's go back to the question. So 1 atmosphere is exactly what's listed as our answer on table A. 15 is 1. They wanted to trip you up definitely because 273 atmospheres, which doesn't really, that'd be way too many, too high, and 273 kilopascals. You know 273 is standard temperature, 273 Kelvin. And the kilopascal should be 101.3. So if you weren't careful enough and you just jumped to what you thought might look somewhat familiar, you might have gotten the wrong number with the wrong unit. So atmospheres is 1. If it was kilopascals, as listed in table A, it'd be 101 kilopascals. 273 is the standard temperature. It's listed in table A as well. So 15 is choice 1. Number 16, a large sample of solid calcium sulfate is crushed into smaller pieces for testing. Which 2 physical properties, okay, are the same for both the large sample, okay, and one of the smaller pieces that it broke apart into? So we're comparing the large sample to one of the smaller pieces, okay. Well, look at choice 1, the mass and density. Well, I know the density is going to be the same for both because density is mass over volume. Smaller volume, smaller mass, that ratio is going to stay constant. Besides, density is a physical intensive property. It's one used for identification. You can't identify something based on mass. And of course, the mass would be different from the large sample to the small sample. So density would work, but not mass. The mass would be, okay, different for the large sample in one of its pieces. So 1's not going to work. And 2's not going to work because you have mass again. Okay, and they're listing volume. Now, volume and mass are both physical extensive properties. These are based on the size of the sample. Okay, so this will not work either because as the size of the sample changes, so does the volume and its mass. The volume is how much space something takes up, and a smaller piece would take up a smaller amount of space. So that can't be the same. Bigger piece takes up more space, smaller smaller particle or piece takes up less space. So for many reasons, 2 is wrong. Okay, if we look at number 4, solubility and volume. Notice volume is repeating since it's an and here. Both have to be true. So using a little bit of logic here. So for one of the reasons 2 is wrong, you can't use volume. So by process of elimination, it has to be 3. And if we look at number 3, they're using the word solubility. Now, solubility is a physical intensive property. It's based upon, well, basically 3 factors. Temperature, how much water you have, so how much water is being dissolved if it's the solvent, and the nature of the compound itself. So because calcium sulfate is an ionic compound, positive, sulfate is -2. Okay, they have strong interactions. In any case, how they break apart into water, it depends upon the three-dimensional arrangement and the attractions, the Coulombic attractions they have for themselves. So different compounds have different abilities to dissolve in water. So solubility definitely is independent, okay, upon the size of the sample. It matters how the sample is attracted to itself and what elements are playing a role. Okay, so that really is an intensive physical property. Density, okay, as we just spoke about, is also another physical intensive property. It does not depend on the size of the sample, depends upon how the compounds actually exist, and therefore 3 is the answer. 16 is 3. Number 17, according to the kinetic molecular theory, okay, the molecules of an ideal gas. Okay, the kinetic molecular theory is a set of conditions that a gas must follow in order to be acting ideally. Now, an ideal gas follows the gas laws perfectly. Our PV over T equals PV over T is a nice calculation where we can calculate the new volume, new pressure, new temperature when conditions change, assuming the moles of a gas stay constant. And the temperature, of course, is in Kelvin. And this calculation works really well when gases are following these 4 basic postulates. Number 1, okay, they're going to be random. And they're random, they go in straight line motions. Think of an ideal gas as an ideal student. An ideal student goes in straight line motions, okay, because they don't want to miss what a teacher is saying. So they would tend to be random when someone speaks to them because they're so focused on the teacher. How you doing? I like turtles. And that's just not going to work in social scenarios. So they're random. They go in straight line motion. So if the teacher asks them to go get a piece of paper or a worksheet from the printer or the back of the room, they would go in straight line motions. And they tend to bump into things. And when they bump into things, their collisions are elastic. Okay, meaning energy is conserved. And number 3 and 4, the most important, because they're so focused on the teacher, okay, they tend to have no attractions for the people around them. So they're not very socially aware, and there's no attractions for the people around them. And 4, they tend to move very fast and have very small volumes, okay? Not trying to paint any stereotypes, but a nice way to think about this. So if you're an ideal gas and you're random, straight line motions, if you bounce into things, you bounce back. And of course, you're small, you go fast, you have tiny volume, okay, and you have no attractions. This would outline the ideal student or the ideal gas, which essentially don't occur in either scenario, but those are what they would have to do to act the most ideally. In any case, they do not have a strong attraction for each other. They have weak attractions, because if they had strong attractions, they wouldn't be moving independently. They wouldn't be random. Have significant volume? No. That means they would be slower moving particles that could attract each other. Move in random, constant, straight line motion. Now, that's the winner. Okay, now why is that important? Because if you were a real gas, okay, if a gas particle is here and you were traveling this way, you would tend to veer off because you would be attracted to that particle. If you were an ideal gas having no attractions, you would just continue on. And being random allows you to follow the gas laws perfectly. So 3 is the best. Number 4 are closely packed in a regular repeating pattern. This outlines a solid. Okay, solids, okay, are not gases. So 17 is 3. Number 18. At 65 degrees Celsius, which compound has a vapor pressure of 58 kilopascals? Okay, well, if you knew this by heart, I would say that you are very, very smart or someone who needs to get a life because there's very little reason why you should know that by heart, unless you like to memorize data, which make you a good Jeopardy person, I guess. Any case, let's go to the reference table that lists vapor pressures for these four liquids. And let's see at 65 degrees Celsius who has 58 kilopascals of pressure. Now, just as an aside, vapor pressure is the force of liquid molecules when they have enough kinetic energy to overcome their attractive forces for each other, can get to the surface and evaporate. When they become a gas, they're going upward, and they produce a collision upward, and that's called the pressure of vapor. Okay, so let's go see which liquid, okay, at 65 produces a vapor pressure of 58. This would be table H. And here we are with table H. And let's go and find our temperatures. Let's go back to zoom in a little bit. And let's go to the bottom. And we're going to find our 65 degrees. This is going by fives, I believe. 50, 55, 60, 65. So there's my 65. And I'm looking for a liquid that's approximately 58 and looks to me like the liquid with approximately 58 vapor pressure has to be this line. Okay, so let's scroll up and we can see that that liquid is ethanol. Okay, and there's our answer. So 8 is choice 2. Number 19. At STP, standard temperature and pressure, which if you didn't know and if you needed it, table A gives you those data. Which 2-gram sample of matter uniformly fills a 340 milliliter closed container? Okay, well, a lot of information here. They said at STP, they told you the mass of the sample. They said, hey, there's a certain size volume of container and all, okay, information that is just not necessary because the key word here was uniformly fills. Okay, and the only phase that uniformly fills, which means it'll fill that container and it'll be the same throughout. It's homogeneous. Okay, is a gas. As gases uniformly fill their container. They take the shape of the container and they always fill the container, right? Even if I just had one gas particle in here, it would fill the container, all right? Aqueous solution is, well, it's in a liquid. They don't always fill their container. And a liquid, for the same reason, doesn't always fill their container. And a solid almost never fills a container, and they have a regular repeating arrangement. So this was just going over the idea that you know how solids and liquids and gases differ. Okay? Even though a gas and a liquid both will take the shape of their container, they have no really regular structure. So they will take the shape, but only a gas with high kinetic energy will fill that container uniformly. Okay? A solid has a regular geometric pattern, okay, where the other ones do not. In any case, 4 is the answer, 19. Number 20. Compared to the freezing point and boiling point of water at 1 atmosphere, a solution of salt and water at 1 atmosphere has, okay, well, you should know there's something called freezing point depression and boiling point elevation when you have solute particles dissolved in water. So a solution will always have its boiling point higher and its freezing point lower. The higher temperature phase change goes higher, the lower temperature phase change goes lower. I always have my students remember this by using one thumb going up, okay, and one thumb going down. This is our secret handshake or signal to get into the chem party. The higher temperature rises, the lower temperature decreases. Anytime you dissolve solute particles in water, and let's say that's the water, that's blue of course, and of course here's my solute particles, these solute particles physically get in the way of this water and make it harder to boil, so you need a higher temperature, that's why it goes up, and they make it harder to freeze, so you need a lower temperature to make it freeze. Okay, So that's what you have to know in terms of colligative properties. So let's read the question carefully, because sometimes I'll get these wrong if I don't. A solution of a saltwater solution has, well, a solution with the solute particles is going to have a lower freezing point depression, lower temperature goes down, okay, and a higher boiling point. They make both phases harder to do. So choice 2. Question we've seen plenty of times. 20 is choice 2. Number 21. Changes in activation energy during a chemical reaction are represented by. I think activation energy, I just think potential energy diagram, where we have the potential energy, we have our time coordinate, and we have, let's say, an exothermic reaction where the reactants have higher energy than the products are more stable, and activation energy is the energy it takes for me to get to the top of the hill. If I want to ride the slide, I have to get to the top. So the energy it takes for me to get to the top of the slide, because once you get past this point, the reaction goes. So the energy that needed to get to the top is my activation energy. And I know, okay, when I'm talking about activation energy, the best way to look about that energy is the potential energy diagram. Ionization energy diagram, okay, it's not part of this course. I'm not sure if I even know what that is, okay. Maybe it's got a different name. Cooling curve and heating curves, okay, those of course we've drawn in other lectures, but the heating curve and cooling curve do not tell you anything about a chemical reaction. They tell you about physical changes, a solid to a liquid to a gas, solid, liquid to a gas, and the phase changes that occur, but they don't talk about chemical reactions. These are physical, so that doesn't make any sense. Choice 4 is the answer. Number 22. Number 22, under which conditions of temperature and pressure would a real gas behave like an ideal gas? So we want to take a real gas and convert it into an ideal gas. Now, ideal gases have two important things here. They ideally have no attractions, right? They're like that ideal student. It's not attracted to other people around them, just so focused on the teacher. A real gas really has attractions for the people around them. They're very, very, very distracted attractions, as we all know. So how do I go from a real gas that really has attractions, like a real student, to an ideal gas that ideally has no attractions for the people around them, just focused on the learning? Again, ideal gas, ideal student. Well, how can I take a real, well, if they really have attractions, they're somewhat close to each other, and they're attracting. So what I'm going to do to go from a real gas to an ideal gas, I want to make them be farther apart from each other, so there's less chance of them attracting. So I'm going to try to lower the pressure on them, right? The pressure is pushing them closer together, so if I lower the pressure, they'll separate. And I'm going to increase the temperature so that they have enough kinetic energy, or they're going so fast they don't have any time to attract. So I'm looking for the lowest pressure and the highest temperature. And that's how I come up with choice 3. Number 22 is choice 3. Number 23, given the equation representing a reaction, which statement describes this reaction at equilibrium? So if we're at equilibrium and double arrows tells me that, the rate of the forward has to equal the rate of the reverse. And because of that, the amount of each of these has to stay constant. As fast as some of this gas becomes this gas becomes that gas. So the amount of each stays constant. Those are the two things you have to remember when dealing with something at equilibrium. Let's go see what choices best fit the description. The concentration of N2O4 must equal the concentration of the other gas. No, they're not going to be equal. If you did a very famous tank demonstration in your school, and your teacher took 2 tanks of water, okay, and he had one with a high amount, low amount, and he had 2 different size cups, and people were pouring back and forth. We got to equilibrium when the values didn't change anymore. The amount of water going from one tank that goes to another, okay, stayed constant. In fact, if you didn't see that, go look at my crash course series, and I do post this. Actually, this is posted on my web YouTube page. Okay, and you can see that demonstration. It goes over this nicely. So the concentrations of each of them are not ever going to be equal. They're going to be constant, and that's what they're saying here. And they are constant because we're pouring the same amount of water into each tank. Okay, or it's going as fast as the forward as the reverse, so the amount of each does not change. 2 is the best answer. 3, the rate of the forward is greater? No, they're the same. The rate of reverse is greater? No. The best answer is choice 3. Number 24. Number 24, which compound is a saturated hydrocarbon? All right, the word saturated means that this hydrocarbon is holding on to the maximum amount of H's possible. Okay, to remember this, table Q is really your friend here. So table Q goes over saturated and unsaturated compounds, even though it doesn't mention them by name. You look at their examples, they give you ethane, which is C2, let's write this here, H6. For 2 carbons, it has 6 H's. Look at the general formula. If I put a 2 here, 2 times 2 is 4, 4 plus 2 is 6. So if you've got 2 carbons, you're going to have 6 H's if you're an alkane. And alkanes are saturated. And the reason why they're saturated is because they hold on to the maximum amount of H's possible. Notice the other 2 carbon systems. This is C2H4 and this is C2H2. Notice as we add double and triple bonds, the amount of H's that are held decrease. Look at this, CnH2n plus 2. If you add a double bond, carbon must make always 4 bonds, so there's less room for H's. Becomes CnH2n. So CnH2n plus 2, you lose the plus 2 as you add a double bond, and you lose another 2 hydrogens as you add in the bond. So this goes from plus 2 to 2n to minus 2. So it goes from C2H6 to C2H4 to C2H2, losing H's. These guys are unsaturated because they do not hold on to the maximum amount of H's because of that double bond and because carbon must make 4 bonds. Any case, so back to the question, we're looking for something that is saturated. I'm looking for an alkane that would fit this formula or have single bonds between the carbons. So I can clearly see that propane is my alkane. The ene is a carbon double bonded and the ine is a carbon triple bonded from table Q. The propanal, okay, is an aldehyde from table R. It's pretty saturated, but it's got this aldehyde ending. Sometimes I call it a chomama group at the end. But it's not as saturated because the carbon double bonded to an O, okay, it doesn't hold as many H's as a propane would because this double bonded O carbonyl group eats up 2 bonds where 2 H's could be. Okay, so 2 is the best answer. Again, the ene from table Q is the double bond. The ine is a triple bond. This was a close second, but again, not as saturated. Besides, what does besides? Hydrocarbon just means what? Yeah, hydrogen and carbon. Propanal has an oxygen, so propane. Number 2 is the best answer. Number 25. The isomers butane and methylpropane differ in their what? Well, iso means same, just like isotope is the same number of protons or same element but different form or different mass difference, meaning they have different number of neutrons. Okay, so heavier or lighter, the same type of element. Isomers, okay, and there's many different types as you would go on to your organic chemistry careers if you do so. But the ones that we talk about in Regents Chemistry are structural isomers, meaning they have the same makeup, number of carbons and hydrogens in this case, but different structures. And these different structures drive their different properties. So butane being 4 carbons from table P, okay, I put 4 carbons there. And I see number of carbons, table P, 4. And I hear the ane part of the butane. The ane tells me there's single bonds between the carbons. And if you need to know where that is to find the piece of information, if you did not know, here it is. In table Q, alkanes have single bonds between the carbons. So in the example I give you, F is 2 carbons, and 2 carbons we get from table P above, and the ane, of course, is single bonds. So butane has 4 carbons, as table P suggests. It ends in ane, so there's single bonds, as table Q suggests, and we fill in the rest with H's. Okay, and you could count if you'd like, and this would be C4, H, and you can count the H's if you like, but I already know that's going to be H10. How do I know? The general formula for alkanes is CN H2N plus 2. So double the amount of carbons, 8 plus 2, that gives you 10 H's. And again, I get that from table Q as well. But if you wanted to do that, there is your butane. Now methyl propane tells me there's a methyl group, which is a 1 carbon group on a propane chain. Prop is 3 carbons. There it is for prop. And the ane part of the propane chain is, again, the alkanes, okay, for the single bonds. All right, so the single bonds, the alkanes. So prop has the 3 carbons, single bonded, but we've got a 1 carbon group from table P, right? Table P tells us again how many carbons. So table P, a 1 carbon group, is a methyl group attached to the propane. So the longest continuous chain is 1, 2, 3 propane. And then we've got a methyl group attached. And we'll put that methyl group right here, CH3. And then you put in the number of H's so that every carbon always has 4 bonds. I didn't mention that over here, but when you draw your structure, now you don't have to do this, you may know this already, but I'm just teaching my little way here. So in any case, if you count the carbons, you get C4H10 as well. Okay, this is a branched hydrocarbon, this is a straight chain. Sometimes they'll put an N in front, but it doesn't matter. If you count the carbons and hydrogens, they have the same amount and type of element. Exactly the same molecular formulas, but different structures. And these different structures, called structural isomers, drive their different properties. So number 2 is the answer. 25 is 2. Number 26. Number 26, which word equation represents a neutralization reaction? Well, a neutralization reaction, okay, is one where the proton from an acid combines with a hydroxide from a base to make water. Now, why they call this neutralization is because by themselves, a proton, okay, is very dangerous if it's in high enough quantities. Strong acids are dangerous because, well, these H pluses are like heat-sinking missiles, these protons for electrons, so they can break down covalent bonds. Okay, that's why they're very corrosive. Okay, hydroxides, okay, are also by themselves, if high enough quantities, also very dangerous. They're used in cleaning agents, and certainly they're used to break down things like, for instance, if you got some hairballs in your sink, liquid Drano will break that down. So individually, these are very dangerous if in high enough quantities, but collectively, if you can actually neutralize and eliminate the danger of these individual bases and acids by dropping an acid or base on each other. So if you match all of the hydroxides in liquid Drano with an acid, you'll make harmless water. And likewise. So neutralization is matching the protons from an acid with the hydroxides of a base. So when you write, okay, an acid-base reaction, this is essentially what's happening overall. Case in point, here's hydrochloric acid, and I'm going to color code this, okay, with NaOH. All right, and what's going to happen is this is essentially a double replacement reaction. If you've done double replacement reactions and understand them, what we have is ions. This is a positive ion, +1. It's a -1. Sodium is +1. This polyatomic ion is -1. So what you're really doing is switching partners. Okay, the Na+1 is going to go with the chlorine, and the H+ is going to go with the hydroxide. So really it's a double replacement. Okay, it's an example of that. So an acid and a base makes the salt NaCl. Now NaCl NaCl, let's do this in red. NaCl is a salt because it's an ionic compound, the positive and negative, metal, non-metal pairing. And then we have what's left over is the HOH, which you can write it like this, knowing that full well that's really H2O, but it shows how these things switch their partners and double replaced. So what we have here is an acid and a base, makes a salt and water. So if you were to mix equal concentrations of an acid and a base, okay, you should get essentially salt water. All right, so an acid plus a base gives us salt in water. And that is an example of a neutralization reaction. 26 is 1. An aqueous solution of lithium hydroxide contains hydroxide ions as the only negative ion in the solution. Lithium hydroxide is classified as, well, lithium hydroxide. Hydroxide is OH minus. And if you don't know that cluster of nonmetals, we would go and look that up on Table E. Table E is what I call the what the heck is that table, because hey, as a cluster of nonmetals, I don't know, Table E is your friend, but you should know that from your acid and base unit. Lithium, okay, is a alkali metal, a group 1 metal, and it's +1. So we can write this, if lithium is +1 and hydroxide is -1, it's LiOH, okay, and it's a base because it dissociates into lithium plus ions, which are spectators, and hydroxide ions. So the only thing in solution that's negative when you drop this in water is the hydroxide ion. This is a definition of an Arrhenius base. It's the easiest definition. People get all bent out of shape when you start mentioning people's names, but you think the only one they actually want you to know by name is the easiest definition. What is an acid? An acid is something that somehow produces H pluses in solution. Hydrochloric acid is an Arrhenius acid. What is a base? A base somehow produces hydroxide. So in your compound, you have to have a hydroxide. That's an Arrhenius base. So don't get all crazy. Since in this question they're asking about the hydroxide is the only thing negative, it's the Arrhenius base. If they asked for the only thing positive in solution is an H+, that would be an Arrhenius acid. It's the most easiest definition. The other definition, which is the Bronson-Lowry definition, which is donating a proton and accepting a proton, they don't ask for you to know that by name. They call it the other definition. So the one is the easiest, okay? Now if you still don't know this, table L and K can help you remind you. And here is table K, and their lists, look at that, H is in front, so they produce H pluses in solution. These are all Arrhenius acids, okay? Look at the Q group, it's the organic acid. Okay, even though the H is not written in front, that H does dissociate away. You can write it this way as well. These are two different examples. This is a molecular formula with an H. This is a structural formula, but they're essentially the same thing. Table L, common bases. Notice the first three here give off hydroxides with a what? A metal. So they dissociate. These are like basically salts, no pun intended, okay? But these are salts that dissociate into their ions. Now, NH3 is not a salt, okay? It's not an Arrhenius, okay, base because you don't see the hydroxide. Now, it is a base because it reacts with water and will take and accept a proton from water, okay? For instance, here's water. It will accept an H from water, and what will it make? It will make right up here, it'll make NH4+, that's the ammonium ion listed in table E, plus a hydroxide. So indirectly it makes a hydroxide by acting as a Bronson-Lowry base, or that other definition. But again, what makes bases is the hydroxide ion. Don't fall in love with the fact, again, not part of the question, I could have something organic, that hydrocarbon chain NOH. This is not a base. That, my friends, is an alcohol. That's not a salt that dissociates. So 27 is 4. Number 28. If you've been following along with number 27, 28 follows right in queue here. One alternate acid-base theory, notice they're saying alternate, they're not giving it by name, by the way, it's the Bronston-Lowry definition they're talking about, states that an acid Okay, well, if you do nothing about Bronston-Lowry, what would be the best explanation? Well, from table K, you have what? HCl. Okay, and from all the acids listed, what do? They produce H pluses. If you talk about the Arrhenius definition, it produces H pluses in solution. Okay, well, a more advanced definition is that not only do I give H pluses in solution, but I can give them to something. For instance, look at a hydroxide. We all talk about that being a base or giving a solution a basic quality. If there's too much of them, the pH rises. Why can't it be neutralized? Well, why does it act as a base? Well, can it accept a proton with that lone pair? And what does it make? Water. So accepting a proton is that other definition. Okay, so an H plus acceptor would not be an acid. What is the acid doing? What is HCl doing? HCl, okay, can give an H to the hydroxide. So it makes sense that an acid is an H plus donor, right? Arrhenius says, hey, it gives off H pluses in solution. The other definition is, well, it actually donates it to them. And you should know something about the hydronium ion, right? Let's get rid of this right here. It sounds like the hydroxide ion, but the hydronium ion is something you should also know that affects the pH. It's synonymous with a proton. So if I have hydrochloric acid again, and I have water, so I have an aqueous solution of hydrochloric acid, what I really have is the hydrochloric acid donating an H plus to the lone pair of the water here, and what you make is Cl negative, a spectator ion. In another course, you'd call this the conjugate base, but of the HCl, but you'll have H3O plus. Okay, and how did that form? That formed because the water accepted a proton acting as a base, and the hydrochloric acid was donating it. So it makes sense that 28 is 1. Acids give off H pluses, so they'll donate them, and bases will be acceptors. Okay, there's no definition with these. So 28 clearly is 1. Number 29. Number 29 states which particle has the greatest mass. So I'm going to look at a table that helps me. And table O I can use for atomic structure, or I can use for nuclear chemistry. They're all about the nucleus. Okay, so the greatest mass is the one that's going to have a greatest mass number. Okay, so if I don't know anything about these particles, or I'm not really sure, table O is a place I'm going to look. Let's go. So here I'm at table O, and you should know your notation. The top number is the mass number. Bottom number is the charge number, or the proton number, if you want to think of it that way. So a beta particle is an electron, high-speed electron that comes out of the nucleus, has a mass of 0 and -1. Neutron has a mass of 1, proton mass of 1. Positron does not have any mass listed, although it has the mass of an electron, which is very, very, very small, 2,000 times smaller than that of a neutron and a proton. Gamma radiation, as an aside here, has no mass and no charge. So of the particles given, the alpha particle has the greatest mass because it's made of 2 protons and 2 neutrons. And since protons and neutrons have the same mass, it gives you a total mass of 4. So the particle with the greatest mass is the alpha particle. And that's why alpha particles compared to beta, okay, or gamma or positron, these are more of a safer type of nuclear reaction because they go slower, they penetrate less because of their heavy, large sizes. So from table O, the one with the greatest mass is the alpha particle, choice 1. Now if you didn't know the mass number was on top of the reference table shows you. I should really say the top of the periodic table shows you. If we zoom in, okay, we get the atomic mass on the top number. Okay, so it's the same notation used in table O. Number 30. A beta particle may be spontaneously emitted from, okay, beta particle. Know where you are in the test, people. Okay, we're at the end of the part A of the multiple choice, the easier versions, 1 through 30. And it goes in order. So we're in the nuclear chemistry section. As you can see, the previous questions we dealt with are nuclear. Number 29 was, now we have acid and base. So we're ending up with nuclear. And you should know that nuclear chemistry has nuclear equations because it's about the nucleus. You have to know this. All of our chemistry, okay, that we dealt with throughout the year pretty much dealt with electrons being transferred if it's ionic, shared if it's covalent. Stability of the atom is based upon, okay, the electron arrangement. Okay, but nuclear chemistry is about the stability of the nucleus. The nucleus has protons and it has neutrons. And when you have more than one proton, how do protons stick together if they're both positive one? It's a binding energy. So there's stability issues. Neutrons somehow buffer, okay, this repulsive force. We don't quite understand it all. There's a strong force that keeps this all together. So the nucleus is what we study in nuclear chemistry, so you'll see notation. Now a beta particle is emitted from unstable nuclei, and there's three different reasons, and there's more than that, but I'm going to break it down to three basic reasons. When a nucleus is unstable, there's a couple of different reasons. Well, the one you have to know for this course is too many protons. If you have approximately greater than 82 protons, there's just too many protons in here in close proximity, and it destabilizes the nucleus. It means it's high energy. So anytime you have instability, you should know it's high energy. So every atom beyond atomic number 82, every single isotope of that atom is unstable. It's nucleus because there's too many protons. So what these guys will do is emit something called alpha particles, which you all know from table O to be 4/2. They're 2 protons, 2 electrons, and you'll lower your proton numbers. Okay, that's not what this is talking about though. A beta particle is another reason why something might be unstable. Now, we talked about too many protons, but you can actually have too many neutrons. Case in point, carbon 12 and carbon 14 are 2 common isotopes of carbon, not the only ones, however. Now, we don't write the bottom number because, well, it's implied. You know, if it's carbon, it is 6, but I'll put it there. So we know that 12 minus 6 gives me 8 neutrons. 14 minus 6, I can do this, I'm sorry. 14 minus 6, thinking ahead, is 6 neutrons, and 14 minus 6 is 8 neutrons. That's how we get that, because protons and neutrons have the same mass. Table O tells you that. Now, this has too many neutrons, or 2 more than carbon 14. This is radioactive. And to lower its neutron number, what it does is a neutron in the nucleus, it's neutral, believe it or not, splits into a proton, which is positive, and a high-speed electron, and also a neutrino, but you don't have to know that. And this electron is kicked out, okay, which is called a beta particle. Notice the neutron splits, the proton number goes up. So what happens is this gives off a beta particle. This is a nuclear equation, okay, 0, E negative 1. I looked that up in table O, and we find this element. What number plus a negative 1 is 6. Notice it went up. 7 plus a negative 1 is 6. And what number plus 0 is 14? 14. Look up atomic number 7 in the periodic table. You'll find it to be nitrogen. And look at that. What had too many neutrons now has the right number. What's 14 minus 7? 7 neutrons, 7 protons, pretty stable. 6 protons, 6 neutrons, pretty stable. So those are some background to why nuclear reactions always occur, or nuclear radiation, which is beta particle, gamma radiation, alpha radiation, positron radiation, always start, okay, from an unstable nucleus to become stable. That's why 30, okay, is choice 4. And again, you could look carbon 14 up in table N, and you'll see that it gives off a beta particle. Okay, table N will list the decay mode. And just for your viewing pleasures here is table N, and there's a carbon 14 nuclei, the actual isotope. And look at the decay node, B negative, which is a beta particle. If you don't know that, table O. Or as I will sometimes say, table O, okay? Any case, the beta particle, there it is, 0 mass, -1, it's a high-speed electron. Okay, there's a symbol, there's the notation. Rock on. Number 31. First question of part B1, the more advanced multiple choice questions that have multiple steps, we'll see. Number 31, which electron configuration represents an atom in the excited state? Well, the excited state represents a scenario where the atom gained energy, okay, and electrons that were in their ground state closer to the nucleus leaped, I should say, into shells that were farther away, as long as they have the exact amount of energy. So therefore, where they were is now missing, so therefore now your configuration is not going in order. Normally electrons go in lower energy, fill lower energy levels first before they go to higher energy. It's called the Aufbau principle. Again, that's not part of the course, but just comes out, sorry. So 2-7 is a ground state that's going in order. Okay, 2-8-1 is going in order. Notice, look, that you can't put an electron here unless you fill the 8. And number 4 is also filling in order. Okay, number 2 is the answer because in order for me to fill the third, if I'm filling everything in order and being ground state, this should be 2-8. How did it go from 2-8 to 2-6-2? Well, 2 electrons from the second energy level, right? The second dash is the second energy, jumped or leaped, okay, into the third energy level and therefore became excited. Now these excited electrons don't stay there. They eventually jump back and they give off the light when they do so, emitting their extra energy. Now number 4 could be bothersome to some of you guys because you'd learn that, hey, in the third energy level, shouldn't I have 18? And you're right about that, but there's something special about those D block electrons, okay? The D, which will fill the third, fills after you fill these. Let's go there for a second, 2-8-2. So 2-8-2 is calcium, and calcium is a ground state atom. And you notice when we go to scandium, you go to 2-8-9. So in this example here, we start filling the third energy level. So this is actually called d orbital, and again, it's not necessarily part of the New York State Regents, although it sort of is. These transitional elements, their valence electrons come from 2 different energy levels, but just for those people that think that this might be excited, it's not. It's kind of a nasty example they give you without giving you the curriculum to totally understand everything going on here. So this third d orbital is in the 4th row, kind of weird, because the 4s fills before the 3d. So it's basically because of overlapping of energy shells. So I know it's a little bit confusing there, but if you're not really sure, see if you can find the element as written, okay, and then you'll know its ground state. No element's going to be written in an excited state, okay? So the best answer, I believe, was choice 2 there. Number 31, choice 2. Number 32, magnesium and calcium have similar chemical properties because a magnesium atom and a calcium atom have the same what? Well, magnesium and calcium have similar chemical properties, and we knew this for many years. Dmitri Mendeleev put his periodic table together by putting elements on cards, and he put them in order of atomic mass. Now, the current periodic table is in order of atomic number. They didn't know about that at the time, but when he put his cards together, of all the elements they known at the time, he noticed that properties started to repeat, so he put them under each other. Okay, and we now recognize that the reason why they were in the same column or in the same group is because they had similar chemical properties, which is based upon their valence electrons. Okay, so if you got similar valence electrons, you have similar chemical reactivity. Okay, let's go to the periodic table to see. Case in point, lithium. Look at lithium, it's 2-1. Sodium, 2-8-1. 2-8-H-1. They all have this one electron outside all of the other core electrons, and that's why they all are in group 1. They all become +1. So these all are very reactive because they're one electron away from becoming stable. The same also goes for group 2 elements. 2 electrons, so forth and so on. So again, the reasoning behind that, same valence electrons is a core concept, same chemical properties. There's similar chemical properties. 32 is 4. Number 33. What is the empirical formula for a compound with the molecular formula? Now, a molecular formula is how a molecule actually exists in nature, whatever structure it has. An empirical formula, you should know, is the lowest ratio. Now they call it an empirical formula because empirically in a study, many different ways we would study compounds, we would do percents by masses, and we do percentages of the different types of atoms in a compound. We would come up only with the lowest ratio. For instance, if we had a 50% ratio of one element to another, that'd be a 1 to 2 ratio, right? 50%, or I'm sorry, if it's 50%, it's 1 to 1. Okay? But that doesn't tell me that's a 1 to 1 atom. For instance, look at H2O2. 50% of all the atoms are oxygen, 50% of all the atoms are hydrogen. Okay, so again, the ratios we would get in the lab do not necessarily mean what they exist in nature. Okay, so empirical is the lowest ratio. Well, we have to reduce. So what's common factor between 6, 12, 2, and 2? Looks like 2 to me. So divide 6 by 2, that's 6, that'd be a 3. Divide 12 by 2, that'd be a 6. That Cl would go to a 1, and the O would go to a 1, which you don't have to write, ClO. So the answer is choice 3, the lowest ratio. That's all that is. Number 33 is choice 3. Number 34. Number 34, given the balanced equation representing a reaction, I can speak. Which type of chemical reaction is represented by this equation? Well, you know what screams to me, party people? I see standalone elements. So as soon as I see a standalone element and I see a 0, I know this is a redox reaction. That means the charges did not change. Okay, well, this charges did change. I'm sorry, can't speak. So what's happening here, if I find a 0, that means that this element's oxidation state is changing from 0 to something else. In this case, it's +3, and this is -2. So clearly it's a redox reaction, but I can identify it by zeros. Now, unfortunately, they don't have a redox listed. Now, if this is a part 2 question, I'd write down the redox. Don't take any chances. But what else do I have here? Double replacement. This is definitely not double replacement. Double replacement means, okay, if you had aluminum with something else and they switched ions, but these guys are by themselves. Single replacement is a classic redox reaction, but we can't single replace here because there's nothing to single replace. You would have to have aluminum, let's say aluminum nitrate, okay, with another compound, and then they can switch spots and single replace with the nitrate. Here, these things are coming together and you're making something. So this is called a synthesis reaction. Okay, we can also call this a formation reaction. Substitution is that organic reaction where we have an alkane that has no room to add anything on, and an H has to come off, okay, in order for a Cl to go on. So substitution is an organic reaction. So the best answer is synthesis. You're making something. Synthesis means making something from its elements. The opposite of synthesis is decomposition, or you could call it analysis. You can analyze what it's made up of if it breaks apart into its elements. So synthesis is choice 4. Okay, I know most of my kids would say, redox, where is it? And some people would think that it's got to be single replacement because single replacement is a classic redox reaction. But look carefully. How can these single replace? You'd have to replace one thing for another. There's nothing to single replace. These guys are both elements making something. Synthesis is the best answer, choice 4. Number 35. Number 35, a person with a body temperature of 37 degrees Celsius holds an ice cube with a temperature of 0 degrees Celsius in a room. So we have a body temperature of 37 degrees Celsius of my person. It's holding an ice cube that's at 0, where the air temperature is 20. Direction of heat flow is always from hot to cold. How do I know that? Heat or warm or high temperatures really mean motion. So things that move fast, okay, compared to things that move slower. Who is going to reach who? Clearly, the molecules with more motion are going to impede and eventually collide and go toward the molecules that have less motion. So heat is going to flow, and when these guys collide, these will move up. Okay, so heat always flows from hot to cold. So we're going to flow from the person to the ice only. No, there's temperature gradients here. Okay, we're going to say the hot, warm body, okay, flows. So from the person to the ice, energy is going to flow, and also from the air to the ice. So the hand is going to melt the ice, and so is the air. So from the person to the ice and air, and from the air to the ice. So from the person to the ice, yes, and air. Oh, I forgot to think about that too, because if we're going to, this is going to be warmer than the air, so the person's going to give off heat to the air as well. So the person's giving heat to the ice cube because it's warmer, and because the body temperature is warmer than the air, it also will warm up the room. So yes, from the person to the ice and air, and from the air to the ice. Choice 2 is the best answer. Now, from the ice to the person only, that can't work. Going from cold to hot. Things that are cold don't move to warm. From the ice to the person, these again, we're going from cold to warm. That just can't happen. You would break science if you did that. Because choice 2 is the best answer, number 35. Number 36, what is the total mass of solute in 1,000 grams of solution having a concentration of 5 parts per million? So 5 parts per million is a concentration formula that we have in table T. Let's go there just to remind you. I know that I wrote it down here for you, but let's go make sure that you know where to look. Table T is the last, okay, reference table in your packet there. And there it is. We have part per million times equals the mass of the solute over the mass of solution times 10 to the 6 or a million. I consider part per million a nothing more than a percent by mass, but a part per million by mass. Mass of the part over the mass of the total. Every time you take a percentage, you take the part that you're looking for over that total to find that fraction. You convert it to a percentage by times by 100. Well, we're doing the same thing here, except the part that we care about is the solute that was dissolved. And the mass of the whole is the entire mass of the solution, which is a solute plus the solvent, which is mostly water in this and our course here. So these two are the same. Percent by mass and part per million are the same, except we're going to multiply, instead of having a part per 100, what a percent composition is, we're going to have a part per million. So this is the same thing. And now, of course, we use part per million because we're dealing with very dilute solutions, okay? And we want to fix a value to a very dilute solution that makes some sense. That's why we make it into a part per million. Okay, back to the question. Okay, so we've got an equation from table T, and we want to solve for the total mass of the solute. So what we're trying to do here is solve for this variable here, the mass of the solute. So let's plug in our values and what's given to me right now. So I know the part per million is 5. I know that there's 1,000 grams of solution, which is the bottom number here. So our X is above, that's our mass of a solute we're trying to find. The mass of our solution is 1,000 grams, and I'm timesing it by my million. I'll put a dot here, not to confuse it here, by my million, which is 10 to the 6th. Okay, so now we're going to do some algebra and solve for X. Now when you solve for X, I'm going to multiply this side, for those that are a little weaker in algebra, by 1,000 over 10 to the 6th, which is a million. Now the reason why I multiply both sides by that is so I can just solve for my X, because 1,000 will cancel and 10 to the 6th. What I do to one side of an equation, I do to the other. So rewriting all of this, I get 5 times 1,000 divided by my million, 10 to the 6th, equals my X, and then we use our calculator. And when you plug this in, X is going to equal 0.005 grams. And that's why choice 1 is the answer. 36 is 1. Number 37. Number 37, which compound is least soluble in water at 60 degrees Celsius? Now, if you are a genius and you already know this, that's great, but most of us have to look in a reference table, and reference table G lists solubility curves. Solubility is the measure of how well a substance can dissolve in a solvent. The solvent we use in this course is water. How many grams? This side of the curve is grams of the substance, and this is the temperature. Most of these curves, all of these curves will go up, okay, because as temperature increases, a solid's solubility, how many grams of it, will increase. So being least soluble would mean we're looking at a particular temperature. Let's say this is 60. We're looking for the curve that is the lowest, the least amount of grams that can dissolve, since solubility is the measure of how well you can dissolve. So we're looking for these four compounds: potassium chlorate, potassium nitrate, sodium chloride, and ammonium chloride. Which one of these has the lowest line at 60? Let's go to reference table G. So in table G, here's my solubility curves. I have potassium nitrate, ammonium chloride, sodium chloride, and potassium chlorate. And let's zoom in here to make some more sense of this. We're looking for the lowest solubility at 60. So here's my line, and it looks to me as if potassium chlorate has the lowest amount of grams. If we were to read this, you'd got around 28 grams of potassium chlorate. Dissolves in how much water? 100 grams of water at 60. So all my three curves, okay, clearly, okay, potassium chlorate is the lowest line. And that's what my answer is. So 37 is choice 1. Number 38. Number 38, at standard pressure, which element has a freezing point below standard temperature? Now, if you didn't know that standard temperature is 273 kelvins or 0 degrees Celsius, you could look here. And there it is in all of its glory, standard temperature. Now they're saying which element has a freezing point below that. Now a freezing point is also a melting point. Now if my freezing point is below 0, think with me for a second. If my freezing point is below 0, okay, let's pretend like negative 40 degrees. Okay, if my freezing point's really low, okay, remember freezing point is the same thing as your melting point, depending on which direction you're going in terms of adding and losing heat. So if something is above its freezing point, okay, or room temperature is normally about 20 or so degrees Celsius, then what does that mean? Well, that means it needs to be at this temperature in order to become a solid. You have to be below your freezing point to be a solid. So if I'm above my freezing point, I'm a liquid. And if you look at your elements, you may not really know too much of these, okay? But you should know that mercury is one of our only liquids. We have two elements that are liquids. One is a metal, and that's mercury, and one is a nonmetal. Bromine is a liquid, okay? So again, if you're above your freezing point, that means, or above your melting point, same temperature, you've melted. Okay, most things, if you're sitting in a chair right now, it's probably made of a metal. And the reason why it's in a solid state is because what? Its melting point or freezing point, okay, is way above room temperature, which means it needs that temperature to melt. Or you're below its freezing point. For instance, if you have a metal that usually have very high melting points or freezing points, well, room temperature is usually lower. Okay, so obviously you're a solid if you're below your freezing or melting point. When you're above your melting point or freezing point, okay, you're a liquid. But if you didn't know that, you can go somewhere to look these up. Okay, and that is, of course, table S. So here I am at table S. Okay, and notice melting points, same thing as freezing. You've got to know that. And of course, I look at indium, 430. Okay, it's pretty high. Hafnium, 2,506. Iridium, 2,719. As we talked about, these are so high. Okay, which means if you are what? If your room temperature is below that, you're going to be solids. You need that temperature to melt. Okay. Now, you say, well, Mr. Grotsky, mercury is 234. That seems higher than 20. Well, that's 20 degrees Celsius. Remember, these are what? Listed in kelvins. So this is below freezing. 273 is what? 0. So 234 is below 0. Okay, so mercury has the only melting point or freezing point below 0. It's the one that's different, but being below 0 degrees Celsius and room temperature is always above that, okay, means that it's in the liquid phase. It hasn't, okay, frozen yet. Or I should say it has already melted, if you want to think about it that way. Being that its melting temperature is so low, it's already melted. These guys need a lot of energy to melt. Any case, mercury is your answer. 38 is choice 4. Number 39. Number 39, which two particle diagrams represent mixtures of diatomic elements? So if I'm a mixture, I know that I'm not bonded. I'm just physically put in close proximity. Okay? Diatomic elements means that I like to bond with myself. Remember the Hofbrinkels that I keep talking about. Hofbrinkels. And maybe your teacher uses a different mnemonic, like Brinkelhof. Okay, H2, O2, F2, Br2, I2, N2. These guys love to bond with themselves. So if you're an element, you're made up of the same type of atoms. We know that's the proton number, but in these drawings, they have to be the same. So if I look at choice B, that's an element, a diatomic element. That could be H2 or Cl2, but this is a compound. So that's a mixture of a compound and an element. Okay. Look at choice D, same reason. Here's an element, a diatomic element, could be I2, N2, or any one of the Hofbrinkels, but here are compounds. Two or more different atoms are compounds. We're looking for elements, a group of the same type of atoms, and they're diatomic, which means they bond to themselves. So A and C make the best case because this is an element and this is an element. They're mixed together, not bonded, and they're diatomic. So A and C are your best answers. Choice 2 for number 39. Number 40, the graph below represents a relationship between temperature and time as heat is added to a sample of water. Okay, I look at this and say heating for water, I see 0 degrees Celsius. Oh, I know this is the phase change. This is where it starts to melt, so a solid is going to a liquid. This must be the pure solid phase, vibrating in its fixed positions. B is when it just starts to melt. C is when it's all completely melted and is now 100% liquid. This is the liquid phase, and this is the next phase change where a liquid is going to a solid. Notice the temperatures are staying constant at a phase change because the temperature, which is kinetic energy, is being converted to potential here. This is an endothermic curve because you need energy to melt and boil. You're going up the energy ladder, and the potential energy is increasing in every single line segment here because we're adding energy to a system. The potential has to go up. The question states, which sample correctly describes the energy of particles of the sample in BC? So this is the point where we have a phase change. Okay, the potential energy decreases. No way. You're adding energy. Okay, heat is added to a sample at a constant rate. Potential energy cannot decrease if you're adding energy. If you give my child some sugar, the potential for him to act out increases. So anytime you're adding energy, the potential energy has to increase. And of course, average kinetic energy, you have to know that that is equal to temperature. The temperature stays constant here. So the potential energy increases and the average kinetic energy, which is temperature, remains constant. And the reasoning behind that is that the kinetic energy, the energy being absorbed at this temperature, is not making them move faster. It's being used to separate them into a phase that has more degrees of freedom. So we're using the energy to pull them apart, not make them vibrate faster. Temperature measures really vibrational motion. Okay, so number 40, potential energy is definitely increasing because you're adding energy. Don't fall in love with the fact it has to go up. Some teachers teach that potential energy only at these segments. Potential energy is always rising. Remember, a thermometer does not measure potential, only kinetic. Number 40 is choice 3. Number 41, given the balance equation representing a reaction, decreasing the concentration of sodium thiosulfate decreases the rate of reaction because decreasing the concentration, adding less of this, will not affect the activation energy. Activation energy, if you remember your potential energy curve, is the amount of energy it takes to start the reaction. So it's where you start to the top of the hill. Got to get to the hill to ride the slide. Okay, but we know we lower that by adding a catalyst, and that would speed up the reaction, but changing the concentration doesn't do any of that. So by having less of this, there are less particles to collide with hydrochloric acid. Don't forget that chemical reactions occur because of what? Because of collisions. So these guys have to collide, and they have to collide effectively. Now, an effective collision is one that has a high enough kinetic energy, motion energy, and have proper orientation so that bonds can be broken and bonds can be formed. So if you have less of this guy, let's make it red, if there's less of these, therefore there's less collisions, therefore they'll be less effective. So take away red particles, the blue particles, if you make hydrochloric acid blue, have less to collide with. So the frequency, which is the amount of something, of effective collisions decreases, which would always decrease the rate of reaction. No matter what you learned in chemistry this year, whether it's concentration, pressure, surface area, catalyst, okay, all those things affect the number and frequency of effective collisions. So how fast a reaction is always based upon how many collisions are occurring. And if you have more collisions, you're going to have more effective collisions. Number 41 is 3. Number 42. Given the equation representing a reaction at equilibrium, double arrow tells me that, which change favors the reverse reaction? So I'm favoring this reaction. That means I'm talking about a shift this way, which means I want a reverse reaction going faster than the forward. This is Le Chatelier's problem. So I'm looking for, okay, which stress is going to make the reaction shift to the left. Now, when I teach Le Chatelier's principle, I teach stress is what we do onto the reaction, and the R is the response of the reaction to regain its balance. For instance, if you're a person standing and I push you in this direction, you'll fall over. Boom. If you don't push back with your feet in the opposite direction to regain your balance. So the reaction is going to respond by doing the opposite always. So let's go through these. If I decrease the concentration of HI, if that's my stress of this reaction at equilibrium, it wants to that'll unbalance the reaction, and it wants to regain equilibrium and its balance by increasing HI. So how does it increase HI? It would shift in the forward direction to make more HI and use up iodine. So that wouldn't work. It would need to go in the forward faster to make HI. Look at choice 2. Decrease the temperature. My stress is to decrease the temperature. The reaction is going to respond by increasing the temperature. Now the heat is on the reactant side. It's important that you recognize that. If I want to increase the heat, I would favor the exothermic reaction, and going in the reverse is the exothermic reaction. I'd make more heat. That's how it would respond. So that's why 2 is clearly the answer. Look at choice number 3, increasing the concentration of iodine. If I increase iodine, okay, the reaction is going to want to decrease it to regain its balance. How does it decrease it? It would use it up, and it would shift it that way, not the way we're looking for. And number 4, pressure. Anytime you deal with pressure stresses, count the moles of gas on both sides. This has 1, this has 1. There's 2 moles of gas on this side, there's 2 moles of gas on this side. There's no effect there. You have to have a gradient, a different number there. So there's no change, there's no effect by pressure. So the only answer that makes sense is choice 2. Number 42 is choice 2. 43. Which form represents 2-butene? Okay, but, okay, from reference table P is how many carbons? So the prefix for the carbons, the number of carbons, that's 4. And the ene from table Q tells me that it's a double bonded hydrocarbon between the carbons. So table P and Q tell me the but is 4-carbon system and ene is a double bond from table Q. So I can look and see that number one, I can just cross off because this is butane. It's a single bond between the carbons. It's 4 carbons, it's saturated, and the ane would mean a single bond. Okay? And so now I've got double bonds. Now, here's the thing. There's 2 double bonds here. This would be a butadiene. This would be a di-2 and an ene at the end. They didn't say 2 enes, just 1 ene. And notice they told me where that double bond was because structure is king in organic chemistry. You change the structure, you change significantly the chemical and physical properties. So 2-butene means on the second carbon we have a double bond. And this would be my winner. If I count this, the first carbon, the second carbon. This would actually be the first carbon, second carbon, and this would be 1-butene. When you count carbons, you have to number the carbons so that the attaching group, or in this case the double bond, is on the lowest number possible. So this is 1-butene. Some people might say it's 1, 2, 3-butane. No, lowest number. So where does the double bond start? In this case, on the double bond, the first carbon. So that's why this is not the answer. This is 1-butene. This, however you want to count it, 1, 2, the double bond starts at the second carbon. 4 carbons but, double bond at the second carbon. Choice 4 is the answer. Number 44, given the balanced equation representing a reaction, during this reaction the oxidation number of Fe changes from, well, clearly this is a redox reaction because I found myself a 0, a standalone element. So I know that it's definitely a redox. It's one quick way. But they're not looking for that. They're looking for what the oxidation number changes to. So we need to know the oxidation state of iron. We know it goes to 0. Every choice is there. But what is it here? Well, here's what we do. We know iron from the periodic table can become +2 or +3. So we've got to figure out which one is it. So here's what we do. We're going to start with the element we definitely know, and it's oxygen. How do I know? Okay, list in your periodic table a -2. So that's your only choice. Now, oxygen can be -1, okay, N+2 in some very, very rare scenarios, but for the most part, always pick -2. So you got one choice really for oxygen. Iron is our problem because iron is +2 or +3, so we can't start there. That's why the problem results. Which iron are we dealing with? That's why we have a stock system. Is it iron 2 oxide or iron 3? Notice I said oxide. It's just with oxygen. So here we go. Oxygen is -2. There's 3 of them. So the overall negative charge due to all the oxygen is -6. This bottom number has to equal 0 because the whole compound is 0. Well, -6 plus what number is 0? +6. And because there's 2 irons, the individual charge, which goes on top the way that I do it, is +3 individually. So it goes from +3 to 0. And it's not about protons, it's about electrons. The entire course is essentially about electrons. Redox. Okay, iron +3 went to iron 0. How did that happen? Because it gained 3 electrons, which we call reduction. So that's all that is, +3 to 0. It got reduced because Leo the lion says grr, gaining electrons is reduction. Number 44 is 3. Number 45, which reaction occurs spontaneously? So spontaneously means that the reaction is going to proceed in a definite direction. So if I'm saying it's spontaneous, the reaction is going to proceed left to right as the arrows are written. So which one actually works? Which one is going to actually proceed? Because if it doesn't occur spontaneously, the reaction does not occur. Okay? So I don't know how you guys might have learned this spontaneous because it's linked to something called Gibbs free energy. You don't have to know anything about that. We have a table that's built on something called net reduction potentials. However, they don't have voltages there, but we have a table that talks about these potential or the ability for things to react spontaneously. Let's go to table J. So table J is an activity series, and they show how metals and nonmetals tend to react. Now metals, the most active metals are listed, and the most active nonmetals are listed. Now we should know that metals tend to lose electrons. So we have a mnemonic, Leo the lion says grr. So metals tend to lose electrons, and this is called oxidation, losing electrons. So this is showing the most active metals, meaning the ones who oxidize the best, the ones who lose electrons the best. So lithium, of all the metals, is the best at losing electrons, whereas gold is the worst. And this should make some sense to you because gold does not like to react. That's why they use it as the ends of a lot of electrical contacts. But also it's a very glimmery, shiny metal that doesn't rust. It doesn't lose its shine ever. Any case, so we've got a list there. Now, on the other side, we have a list of who gains electrons the best, who reduces. And F2, being the most electronegative atom, of course, is the best at gaining electrons. So, when you're dealing with metals in a reaction, and to see if it's spontaneous, the ones who oxidize have to be above the ones who reduce in order for the reaction to proceed. So we're not going to ever have an element that's poor at oxidizing going to oxidize when there's an element there listed that could oxidize. It's better. Whatever you're good at is what you do. So if lithium and barium are present in some aspects in a redox reaction, the lithium is the one who's going to oxidize if it's a metal, and the barium, if it's an ion, is going to reduce. So we've learned the one who is oxidizing is above the one who's reducing. And we use this in electrochemical cells, in voltaic cells. If I've got potassium and cesium, okay, as my electrodes, the K is the anode, anox, because K is the one who oxidizes best. Okay? Now over here it's flipped because we have, of course, you have your metals. Okay? So nonmetals. Nonmetals tend to gain electron. That's why they reduce. So in this case, if you're dealing with a nonmetal reaction like our question is, the ones who reduce are above the ones who oxidize. Okay? So if you have two choices and they're all nonmetals like your question, the one that's better at reduction is going to do so. And the one who's not is going to be forced to oxidize. And that's important. Okay? It's flipped from this side. So let's go back to the question. So you can see that I have a bunch of metals and nonmetals here. And let's see what we're going to say. Which reaction occurs spontaneously? Let's get some stuff out of the way. Let's look at some charges here to see what's going on. We know chlorine is a 0 and it's becoming a -1. Now in this case, okay, if chlorine is becoming a -1, its charge is going down because a chlorine gained an electron to become Cl negative. This is reduction. Now, who's getting reduced? Who's getting oxidized? If something is getting reduced and gaining electron, something's losing them. Now, sodium is +1, sodium is +1, so it doesn't partake in the redox reaction. It's a spectator. Bromide is -1 because if sodium's +1, bromide's -1, and if bromide's by itself, it's 0. So Br negative, in this case, is becoming Br0 when it loses an electron, and this is oxidation. So, if this is spontaneous, I would need the chlorine to be above the bromide because chlorine is the one who reduces. Let's go see if that's the case in Table J. Lo and behold, chlorine is above bromine. So, nonmetals, they're best and most active when they reduce. So, this guy's going to reduce, and the bromide or some form of it is going to oxidize. And that is the case of my half reaction. So choice A is the answer. If you look at the other answers, the one who reduces is not above. Notice this also goes in order of the group. This is exactly how it is written, okay, in table 18. Atoms get bigger, they become less ability to gain electrons. Let's go over the other one more choice to see an example of why it's wrong. So we know 45 is definitely choice 1, okay? But let's go over choice 2 to show why that would be wrong, and the others would follow suit. So chlorine is 0. It's becoming -1. F is -1, so it's becoming 0. And if we draw our half reactions, let's get some space here. Whoa, get that out of there. We're going to have chlorine. Okay, that's too much blue for me. So we got chlorine 0 going to chlorine -1. Notice both sides of a half reaction have to have the same charge. The electron goes here, -1 and 0. And then we're going to have fluorine, okay, -1, give up an electron, oxidize, and become F0. That's what I'm doing here. This is reduction. So in number 2, we've got chlorine who's reducing and F negative who's oxidizing. Well, is that going to happen? If I really have fluorine gas around, isn't it better at reducing? Well, let's go see. So according for this to work, chlorine has to be better at reducing than fluorine. Clearly this is not the case. Fluorine's better at reducing than chlorine. So that's not going to work. You're not going to have fluorine there, okay, and it oxidizes when it can reduce. So that's why the one who reduces on this side has to be higher than the one that oxidizes. It's the opposite for the metals. Okay, next question. Number 46. Number 46, which sample of HCl contains the greatest number of moles of solute particles? Let's see here, party people. We've got molarity. We're looking for moles. We need a formula for molarity for me to figure this out. Let's go to table T. Okay, so in molarity, or in table T, sorry, molarity is moles of solute over liter of solution. Molarity is the big M that you see. So if you see the word, if you see the letter big M, or you see the word molar, it's talking about this molarity formula, which is moles of solute, the substance being dissolved, over a liter of solution. That includes the water and the solvent. Okay, so molarity, big M, is equal to moles of solute over a liter of solution. Okay, so we're looking for solve which one has the greatest number of moles. Okay, so I guess you could go through this one by one to get this, or you can recognize which would give you the greatest. But when you solve for moles, let's rewrite this. We're given the molarity and the liters. So we're giving these two variables. When you solve for moles, just by some basic algebra, it's going to be molarity times the liters. So if it's that simple, then multiply these two together. 1 times 2, this would give us 2 moles. 2 times 2, 4 moles. 3 times 0.5, 1.5 moles. 4 times 0.5, 2 moles. And the one with the greatest number of moles, of course, is choice 2. Now, how do I get moles out of that? Well, molarity is moles over liter, right? That's what molarity is. And here's a liter, which is a liter. And then when you solve for moles, the liters cancel, and that's how we get the moles. So it's just solving for the moles, noticing, observing that you have to have the molarity formula. 46, choice 2. Number 47. Which change in pH represents a 100-fold increase in the concentration of hydronium ions in a solution? Hydronium is H3O+. It is synonymous with H pluses. Now, if you didn't know what a hydronium was, table E shows you. And there it is, hydronium. It's a polyatomic ion, a cluster of nonmetals. Okay, we know what the hydronium ion is. You should know from concept it comes from acids. Acids produce H pluses. H pluses sometimes are donated to water to create this water with an extra proton. But essentially, we have an acidic solution. So we have a 100-fold increase in the concentration of an acid. So our pH is going to drop. You should know from a 7 to a 14 range, okay, I won't say basically, okay, is a base solution, and anything lower than 7 is acidic. Okay, something you need to know. And the reasoning behind that is because the concentration, let's say 1 times 10 to the negative 5 concentration for the hydronium. What's the pH of that? Well, you should know from your chem classes and your teacher, the pH is the negative log of this, which is really the positive value of this exponent, if there's a 1 there, of course. So the pH is 5. If you make this increase, okay, 100 times, let's make this number increase 100 times. Now what I have is 1 times 10 to the negative 3. Yes, this concentration of hydronium ions, or H pluses, they're synonymous, is 100 times bigger, right? This is 0.00001, and this is 0.001. This number is bigger by 100 times. And the pH of this is a pH of 3, positive value of that exponent, assuming that value there is 1. In this course, it always will be. So our pH dropped 2 integers when we got acidic by 100 times. So I'm looking for a pH to drop by 2 integers, and that would increase 100 times because these are logarithmic changes, right? Each integer is 10 to the 1. It's a movement of a 0. So if you have a 100-fold increase, you know that 10 to the 2 equals 100. All right? So I'm looking for 3 going down to a 1. That changes by 2 integers, which means 2 exponents base 10, which is 100 times. And it's getting more acidic because my pH is dropping. So choice 4 is the answer for number 47. Number 48, which indicator would best distinguish between a solution with a pH of 3.5 and a solution with 5.5? Okay, so I'm looking for a chemical indicator, which is a weak acid-base pair that color changes in different pHs. Okay, so I want to distinguish between 3.5 and 5.5. They should be 2 different colors. So which indicators, okay, have a distinct color change between these 2 pHs? Well, table M is a place where we can look. Let's go there. So here is our table N, our common acid-base indicator table, and how it works is very simple. If you have a red color, that means you're 3.1 or lower. If you have a yellow color, you're 4.1 or higher. So I'm looking for an indicator that's going to give me a great change here. So my choices are, our choices that we have are the ones I've just checked, okay? And if I look at thymo blue, it goes from yellow to blue. Well, these pHs are below 8, so both of them would be yellow for thymo blue because they're both less than 8. Brome crescel green, well, let's see, 3.5 is lower, good, that'll be yellow. And then 5.5 is above that. So I like, that is a strong possibility. Okay, so blue and yellow. Litmus, they're both less than 8.3. Okay, 5.5 is going to give me some color in between, not a drastic color change. And then bromo-thymo blue, okay, well, they're both less than 6, so they both be yellow. So litmus and brome crescel will give me the best choices, but this purple to red is still very close. Nice yellow to blue color change, okay, would be the best answer. This is 3.5 is less than that, so we'll have a nice yellow color for the 3.5, and 5.5 is above 5.4, I can speak, and that'll be blue. So nice distinct color. Here there might be some distinct. However, if anyone's dealt with litmus, it's a peachy color, sort of in between, hard to distinguish. So brome crescel green is our clear winner in distinct color changes. So number 48, choice 2. Number 49. All right, number 49 is a little bit of weak acid-base theory here. I have an acid as denoted by the H in front, or table K, all right, and then I have water sitting here, all right. Now, I know that after the acid donates its proton, that's what they do, according to the other theory, okay, what's left over, we call it a conjugate base of the acid, okay. So I know from going left to right that the HCl donates an H+, whether I go to the table or not, because in the forward direction, this Cl compound doesn't have the H+ anymore. Notice it's negative, so it's missing it. So this guy had to absorb it. So H2O with one more proton becomes something called the H3O+ ion, which is called a hydronium ion. Now, if you didn't know that was the hydronium ion, table E we go. And there it is in all of its glory, the hydronium ion. So 49 is choice 2. Number 50. Which nucleide is used to investigate human thyroid gland disorders? Wow, this is by far the question that is least chemistry-like. This has nothing to do with chemistry. This is just information that you should have learned at the end of your nuclear unit. Carbon-14 is used to date organic compounds because of its long half-life. It's a beta emitter. Cobalt-60 is either used to identify brain disorders or chemotherapy. Okay, it's long, it's pretty nasty stuff. Iodine 131, okay, is something that we may use, and in fact, it is the answer. Now, the thyroid gland uptakes iodine. It's something you may have learned from biology, and if you don't have enough iodine in your diet, you'll get something called a goiter. Your neck will actually get really, really big because you have your thyroid glands on your neck. Okay, we've eliminated that by putting iodine ions in our table salt. So if you ever looked at table salt, you'll see that it's iodinized. You'll see that word. There'll be a little sodium iodide. But if you still didn't know any of that, you could look on table N, and you would look for the shortest half-life, right? The shortest half-life is something that you want to investigate on humans with because it gets out of your body pretty quickly with a short half-life. So let's look at these elements in table N and see who has the shortest half-life. So here is table N, selected radioactive isotopes. Carbon-14, big half-life, okay. Cobalt-60, a beta emitter, not something else I want in my body, long half-life. Okay, Iodine-131, 8 days, that's cool. Potassium-37, we may say, well, why don't we use that? It's got the shortest half-life. Well, it may be what? Too short, which means but it may decay into nothing before you can even look at the monitor. So we inject people with the nuclear medicine, and then we want to be able to find out, trace where these compounds are when they give off particles. Well, if this thing has a half-life of 1.23 seconds, the guess is that I bet it would, in a matter of seconds, okay, disappear from the body and you wouldn't be able to detect it. This half-life is short, but long enough to stay in the body long enough to diagnose. So you could have figured that out from table N, iodine 131. So choice 4 is the best answer. This concludes the multiple choice. Yippee! Now, follow the link. You can go on to the free response part of the test for more of the Grodzki solutions. Rock on.